Okay, great. Thank you very much. And I am sorry I couldn't be there in person. My visa didn't come through. So I'm going to be talking about dynamic imaging. And for me, this kind of started as a bit of an adventure story, because back during COVID, we had this completely crazy idea of trying to observe OH masers on Callisto as a probe for water on icy moons. And of course, if you're going to observe Callisto in the radio, then you need to deal with Jupiter, which is a very bright radio source. And so we thought, well, hang on, we've got some commissioning observations of Jupiter. Why don't we look at those first and, just see if we can image Jupiter decently? And turned out there was an observation of Jupiter done during the Great Conjunction. And, well, the thing about planets is that planets move. And so as soon as you start imaging a bright planet like Jupiter, instead of you doing a normal deep continuum image like I'm used to doing, you have to make a movie. So we made this little movie of the conjunction, and I call this, it's a very fun movie. I call it Astronomer's Bingo. Usually I play a little game. I don't have time to play a game here, but you can play a game with optical astronomers where you ask them to identify what are the interesting things they can see in this movie. And there's quite a few, right? You can see Jupiter in the center. Telescope is tracking Jupiter, so therefore the rest of the sky is spanning past. There's, turns out there's a couple of AGN joining the conjunction. So the conjunction on radio was a lot more interesting than the conjunction on optical. Usually people can eventually work out where is Saturn. Of course, it's this thing here, because it's also moving relative to the background objects. You can see Jupiter's polarization, magnetic field here. That's a nice little boring dipole, because of course we had polarization measurements. And we even detected Callisto up here in this inset. If you do a 5-scan mean of 5 frames, that little dot is exactly where Callisto is predicted to be. So we haven't detected OH yet, but at least we can pick up Callisto in radio. But the really cool thing was there was still a surprise in this image, and that was in the circle here at the beginning of the movie, in this yellow circle, you can see a thing popping up. And this was obviously transient. Turned out to be a very mysterious transient. It was 6 millijansky at the peak, on for 45 minutes, wide band, 100% polarized, had a rotation measure that was consistent with the Opperman map. And we puzzled for quite a while what this thing could be, and we even got follow-up time at the same location. And in the follow-up, here's a more regular MeerKAT image in UHF of that same field in the follow-up. Of course, Jupiter and Saturn have moved off, but we can still see our little source. It was a variable source. It was kind of bubbling up and down. Took us a long time to work out what it is. There was a theory that it was like a brown dwarf or something, so we were looking at dwarf flares. And then the MeerKAT people, the pulsar search people, who are observing commensally. Anytime you use MeerKAT, the pulsar search engine is on and it's looking for pulses. They called us up and they said, hey, we're detecting some pulses in your observation. And they sent me the time steps of the pulses. I compared them to the light curves I was getting from the source, and we discovered, oh, they're detecting pulses at the same time as we have peaks in the light curve. So then the penny dropped. We realized, okay, this is actually a pulsar of some kind we're looking at. And we did a full deep observation with the pulsar timing engine and observed these lovely dynamic spectra for this object. These are very weird dynamic spectra. Individually, none of them are weird because they show scintillation, and pulsars are supposed to scintillate, as we know. But if you compare the spectra hour to hour, they are very weird because scintillation is not really supposed to change character like that on hourly timescales. So we still haven't figured out what the subject is. At least we figured out what to name it. I was going to name it an ERAT. Well, I thought it was an ERAT for a long time, and I was very disappointed when Ben Stoppers told me definitively that I'm not allowed to call it an ERAT because ERATs are supposed to be truly off when they're off, and this thing is never off. It's just going up and down. It would have been nice to call it an ERAT because, of course, my research group is called RAT, so the RAT ERAT had a pleasing ring to it, but we got a better name in the end. We called it a parrot for pulsar with anomalous refraction recurring on odd timescales. And you can find the paper here, which is also a very nice name because, of course, the Rat and Parrot is an infamous pub on campus where it could be fairly considered maybe the birthplace of MeerKAT, because Justin Jonas was quite a regular of the Rat and Parrot. So anyway, that was a nice bit of work, and that kind of got me into the transients business. And then I was triggered by Ian Haywood, who gave a lovely talk at the MeerKAT at 5 meeting. And he proposed that what we should really be doing, we should be building 2 robots. We need one robot that's moving backward in time and mining the MeerKAT archive for these things. And we need a robot that's moving forward in time and doing commensal transient searches on any MeerKAT observations that are going on. And these things, of course, are very different computational problems, right? Because if you want to mine an archive, you can have something that's relatively slow, but it can be massively parallel, because it's a completely embarrassingly parallel problem. If you want to do commensal transient searches, you need to think about real-time or near real-time work. So very, very, very different problems. But that kind of got us into that same field, and we got support from Breakthrough Listen for this, and we started a project called Fatale, which is basically dedicated to dynamic imaging and transient searches with MeerKAT and with HA. The eventual aim of this project is to mine the entire MeerKAT archive for more parrots, more overlooked transients. And there's kind of a holy grail and a stretch goal is the near real-time search. And of course, near real-time transient search would require near real-time calibration and imaging, which, as you all know, has never been done yet with any radio telescope. So that's why I'm calling it a holy grail. Or maybe I should call it science fiction, because it's still a very hard problem. But where we are now, having started about a year ago, what we're doing is we've processed validation fields. Like, for example, we have data of the parrot. We know there's a transient sitting in the field, so we can test it with our pipeline to see that at least we can detect it. We've processed some MeerKAT data of promising fields, things like globular clusters, galactic center, galactic plane, things where you kind of expect to find more transients than in other places. We're also doing things like, for example, if RAT students are calibrating and imaging data for their own project, whatever that project is, I usually ask them to run the transient pipeline in the background. Because as you'll see, what the transient pipeline requires is well-calibrated data. So if you're sitting there calibrating data and you've got a nice map, well, you're ready to push the button and run the transient pipeline on that. And we've also started some targeted searches, so looking in archive for specific interesting classes of objects. So, for example, finding all the exoplanetary systems that happen to be in a MeerKAT field of view and starting the search there first. So that's our approach. How this is done, we've developed a new pipeline called TRON, or Transient Radio Observations for Newbies. The way TRON works is, like I said, you have to start with normal calibration and imaging. So in fact, this is crucial. Your transient search is only as good as your calibration. And there are many other problems to solve, even if you have well-calibrated data. So you start with calibrated data, and then you run the pipeline, right? And what the pipeline does, it subtracts model visibilities from the data. It takes the residuals. It images them at the raw time cadence, so 8 seconds or 2 seconds in the case of MeerKAT. Now you've got thousands of residual snapshot images. Ideally, they're going to be noise-like, but I'll show you in a second what they really look like. Now you smooth these images to various timescales, you compute power spectra, forward diff, whatever. And then you look for stuff. You look for stuff that varies or the stuff that pops up along the time axis, effectively at every pixel in the image. And then for all the detections and all the interesting objects in the image, you extract light curves, which gives you tens of thousands of light curves per every observation. Make dynamic spectra for the really interesting things like detections. This is a relatively expensive operation, so you only do it for a few interesting objects. And the thing I want to stress is that we kind of casually call this kind of thing data reduction. Well, when you're doing this, it's definitely data non-reduction or even anti-reduction, because you start with terabytes of visibilities and you end up with terabytes of image cubes. So it's not really any sort of reduction. What this meant is that we have a whole lot of software problems that needed to be solved. You cannot handle terabyte cubes in fits. Well, I mean, you can, and spectral line people have been doing this, but when you're doing spectral line work, you're usually looking at a small subset in frequency, so you have much more benign data access patterns to your fits cubes, so you can kind of get away with using fits. When you're looking for transients, you've got an irregularly sampled time axis. Your data access patterns are you're going in time, then you're going in space, so fits is just because it doesn't work anymore. So basically, we've had to develop a whole new data stack for Tron and a whole new software stack with new data formats. Fortunately, there's some very nice developments in the Python world which made this easier. And I won't go into too much detail because this is not a software talk, right? It's a science talk, but you see them listed here. So Tron is, because of all this, Tron is relatively efficient. So we can do a transient search in, if you have a few hours of observing time, Tron will run in roughly those same few hours. So you can think of it as near real time, except of course you have to do the self-call first. So once you've done the self-call, the transient search takes a few hours for a few hours of observing time. So we're kind of, this makes me reasonably optimistic that maybe someday we will have near real-time transient detection on some radio telescope. Of course, once you start rolling out the time axis, you find out, this is a question that Jan Noordam raised. He used to like to ponder this question, what's buried in the noise? And turns out you can bury a lot in the noise. When you're averaging, you are writing many sins, and you can hide a lot of sins under the time axis. When Jan was pondering this common in-joke, we were saying that what's buried in the noise is the bones of Jan's enemies. And now turns out the joke was on us because Jan is actually a nice man and doesn't have that many enemies. What's buried in the noise is a lot worse. So I can show you an example. Here's a parrot field, right? Here's one of our follow-ups on the parrot. You do self-call an image and you get a perfectly beautiful MeerKAT map. You say, okay, great, I've got a noise-limited map. I can proceed to hunt for transients. Let's open up the time axis. And you open up the time axis and you see this. So that's what the residual 8-second snapshot image looks like. What you're seeing here is, I think, one of the bright sources, this bright source here. And this is, I expect this is just ionosphere, because from time slot to time slot, your bright source is doing this, which is, as you can imagine, pretty annoying when you're trying to find transients in that field. So it's basically ionospheric scintillation. So now you're looking for interesting things in this kind of map, and what I've got circled here, that's actually the parrot. Because we know in this follow-up field, we know where the parrot is. It's there in that little red circle. Here's a little zoom. You can actually see it's a nice little compact source, but it's pretty hard to pick it up over these side lobes that are jumping up and down. And this is the parrot in a time slot when it's flashing up, and this is a parrot in a time slot when it's flashing down. So kind of not, as you can imagine, it's not too easy to kind of pick this up automatically. But we do have a detection algorithm called Bryfast, which seems to work quite nicely, even with horrible residuals like this. It's actually based on an automasker that Cyril Pass wrote for the Loafer pipeline a long time ago. So what Bryfast does, it searches for transients, searches for variables at multiple time scales, starting from the raw time scale, and then in steps of 2. So from 8 seconds to 15 seconds, 30 seconds, 60 seconds, etc., etc. And it's heuristics based. So there's additional heuristics to reject artifacts, to reject RFI, and so on. There's also machine learning approaches that other people in the group are exploring, but they're not quite mature yet, so I'm not going to report on them here. And the nice thing about Bryfast, well, the first question for us, can we detect the parrot automatically with this algorithm, automatically and blindly? And turns out, yes, we can. We have detected the parrot reliably in every single follow-up observation where it was flashing at us, detecting it about 8 sigma. And I should actually fix the slide because in L-band we detected as well after with the new version of Bryfast. And the other nice thing is that we've got no false positives, even in horrible images like that. So basically, you run Bryfast on that observation, and the only thing it gives you is the parrot. So of course, the next question is: are parrots everywhere? The answer, unfortunately, is no. The universe is not that kind to us. So you're not finding a new transient in every field we look at, but we have been finding some very nice stuff, and I'm going to take you through it a little bit briefly. So this was, I think, the first thing we published. These are the global cluster fields that I said we've been processing. So we've processed 3 global clusters, and we've detected millisecond pulsars in all of them. So you can see on the left here, this is Omega Centauri, and that's what's circled is the singletron detection in that field. And you can see the light curve. This is a smooth version of the light curve of that object. It's very nicely regular because what this thing is, it's like it's a black widow. It's an eclipsing pulsar. So it's a pulsar with a companion, and there's an eclipsing going on at time scale of about 2 hours. And that's what gives us the signature, the variability signature in the image plane that Tron is detecting. On the right here is 47 Tucana. Here we're picking up 3 millisecond pulsars with corresponding light curves. These light curves look a bit different because they are, what's going on here, it's not eclipsing, it's scintillation. So it's scintillation on fairly slow timescales, on hourly timescales, and that's what giving us the light curve excursions, which allow us to detect these pulsars. On the next slide, I've got the dynamic spectra for these detections, and for another detection we made in the 3rd global cluster, which was Terzen 5. So a dynamic spectrum, of course, is flux as a function of time and frequency. Well, I would say differential flux because remember we subtract the model, so we're only looking at, say, the differential brightness in each pixel. And you can see, like on the left here, these are the eclipsing millisecond pulsars. You see very nice eclipsing behavior, and on the right are the scintillating millisecond pulsars. Although I think the one on the bottom, if you squint at it hard enough, you actually see a fairly regular alternation of the red and the blue patches. So you think this one might also be eclipsing, plus scintillating on top of that. So this was very nice. This was kind of our first proper detections. Then I found a little surprise in one of the parrot fields. So remember, I told you we detected the pulsars with the parrot with no false positives. Well, there was what I thought was a false positive in one of the follow-up fields. Turned out to be not a false positive. Turns out it's a real object. So this is what this is. This is a Gaia star about 1,300 parsecs away. It seems to be an RSCVM binary, and basically we detected a flare from it. So in that same field where we were looking at the parrot, there was a nice surprise that there was a second transient sitting there. So it's a stellar flare. Again, it's very highly circularly polarized. Here's the light curve. Here on top you see the dynamic spectrum. The fact that it's circularly polarized suggests it's electron cyclotron mason stability as the mechanism. And you can find a paper here down at the bottom. So those are the 2 things that you can find published. I can show you preliminary results of things that haven't been published yet. This is what we call the Koi M-dwarf. So this is old MeerKAT data. This is the Sargent MeerKAT galaxy plane survey. So it's data from 2019 or something. And one of our students has been reprocessing that data to make deeper images for his project. He needed to make higher dynamic range images of some of the pointings. And in one of the pointings, he picked up again a stellar flare. This seems to be a nearby M-dwarf, so quite nearby for a change, 20 parsecs. It's actually a candidate exoplanetary system. The funny and kind of annoying thing really about this observation, so this was observed as a mosaic and as a relatively quick mosaic. So the telescope was spending several minutes per pointing, and then it was going on to do another pointing. And when we construct the light curve of this dwarf, you can see what happens here. This is the one scan where we detected it. So you can actually see the flare picking up, and just as the flare starts to peak, boom, the telescope moves to a different pointing. And I'm showing here, since we can compute the primary beam gain of the telescope, the other pointing is nearby, but of course now we're too far away to see the flare. And then a few minutes later, we return to this original pointing, and just as the flare is settling down. And then as it picks up again we move to another pointing. So we call this the Koi dwarf because it seemed to be flashing at us whenever, I don't know, maybe it's extraterrestrial intelligence. They knew when we were looking at them, and they were only doing the flare when we weren't looking at them. The other very nice result we have in the pipeline is this. And this one was a true puzzle for a while because if you look at the dynamic spectra of this object, well, now we think it's a pulsar. When we saw this dynamic spectra, we didn't know what to think, right? Because, again, look at the time and frequency behavior of this object. We were joking that this looks like an alien FM radio station, right? Because you have these bands of emission which are fairly monochromatic, which kind of persist, and then they switch off, and they start at a different frequency, and then again they switch off and start at a different frequency. So something very, very weird. But we got, this was 2019 imaging data, picked up this detection withdrawn, and then of course we immediately asked for some follow-up time, and we did a follow-up with UHF and with a full pulsar timing engine. So with the pulsar timing engine data, we're kind of beginning to disentangle what it is, although there's still more questions than answers. So this is a pulsar, well, a millisecond pulsar technically. It's got a half-second period, but there's more periods in the system, right? So it's got a half-second period, plus on top of that, it's got a super stable 5-second or close to 5-second dropouts. So every 5 seconds, there's a drop, and that's super regular. And then on top of that, there's a somewhat irregular quasi-periodic period, 55 to 65 seconds, which is what you see here in this dynamic spectrum, right? This is several hours, so that minute period is kind of seen as the vertical banded structure in this image. And on top of that, you have this strange scintillation signature, which, you know, in a short period of time, this dynamic spectrum is not strange, right? Because pulsars scintillate, so you can expect a strong chromatic behavior. What's strange is that it persists for a few hours and then it seemingly switches, like almost digitally, to a different scintillation behavior. Like you can see between here and here, there's a switch in the scintillation properties. So, I mean, at the moment, we're still really scratching our heads over interpretation of this. There's a lot going on here, and but what I like about this result is this is pretty much the, you know, the second time we find a new pulsar, and it's also a very weird one. It's also a parrot of sorts. So I think these image plane search methods must be biased towards finding really weird and wonderful objects, which is great. And here's another neat result I had recently. So I think I saw Dharam in the list. So I think Dharam is an audience. He will remember these images. This was an observation we did back in 2020, first open time. This was a project with Bernie Fanerov. It used to be called Old Devils. Then for the publication, we changed to Old Friends. It was basically a study of four very bright radio galaxies. And for one of those radio galaxies, I could not make a decent high dynamic range image no matter what I tried, which was a bit of an affront because I'm supposed to specialize in high dynamic range imaging, and I just couldn't do it with this particular galaxy no matter what I tried. So you can see here is an honestly saturated map to show you that really we could not achieve dynamic range on this thing. And of course, now that I'm 4 years older and 4 years wiser, and I have a transient search pipeline, I thought, wait a minute, let me search the pipeline, let me run the pipeline on this thing. And I got this very exciting light curve from the AGN core. It looked like that. And for a little bit, I was very excited because I thought, wow, this is, okay, of course I can't get a high dynamic range image because the AGN core is booming up and down like this. You know, if you've got time variability in your brightest source in your map, you cannot expect high dynamic range. Brilliant. But why is the AGN core so variable? And then I started eyeballing the residual cube at the positions where the AGN core was doing this. And I found this. So these are the animations of those periods where the AGN core is going up. And you can see this thing flying through the field along the same track in both instances. So in the one instance, it's pretty faint. Going here, over here, it gets super bright. So of course, we called it a UFO because it took me a little bit of time to identify it. Until that point, it was literally an identified flying object. But now I think I worked out that this is actually just Galileo satellites. So it's really just bad luck that we picked a target that was right on the day of observation. That target was right next to the orbital plane of one of the Galileo orbital planes. So twice in 4 hours, we got buzzed by Galileo. So on the one hand, it's bad luck. On the other hand, you can think, well, actually, maybe this is a little bit deterministic, right? So we actually need better tools to tell us when we've got satellites in our field. We also had an interesting example of this in the galaxy plane survey, because these images were coming out very poorly until we did transient search and started looking at light curves and realized that in that mosaic, some of the dishes still hadn't settled when the telescope was observing. And we could clearly see a signature of that in the light curves of all the sources. So we only needed, Athanasius only needed to flag out the suspect time slots to get a much better quality image. And this is the sort of thing that kind of becomes obvious, basically pops out at you once you start doing dynamic imaging and once you start doing light curves, but it's not obvious when you're just sitting there trying to self-calibrate a pointing in a normal way. And same here, I was self-calibrating this thing into submission and wasted hours of my life, but as soon as I made a dynamic image, it's just satellites. And I mean, this is easy to deal with, right? All I have to do is flag these time intervals. And yeah, by the way, what's happening on top of this is that the satellite is coming through, so it's messing with the gain solutions, so that's leaving an imprint on the AGN and on all the other sources in the field, and that's what's causing the dynamic range to be very poor. And you really need to know, well, to deal with this, you really need to do really dynamic imaging, because this kind of thing, particularly this first Galileo pass, you can see this is just an extra bright source that's passing through the field. This is not going to raise the suspicions of any flagger, so normal flagging just doesn't help you in this situation. Okay, anyway, I think I'm coming to the end of my talk. I think I would like to leave you with my conclusions. First conclusion is that MeerKAT is an absolutely fantastic instrument for these kinds of searches because you have fantastic instantaneous sensitivity. So if you're looking for faint transients, for faint and fast transients, it's really, I think, the best instrument that will be able to find them. Dynamic imaging is hard. There's a lot of bones hiding in the noise, but it can be made to work with some effort, and it's certainly worth it, both in terms of the science payoff. You can see what we've already detecting in less than a year, but also feeding back the results of that into your normal continuum imaging can improve your regular imaging. And our pipeline shown is ramping up, so stay tuned. Hopefully I'll have more results to talk about next time I deliver a talk like this. And finally, I'd like to leave you with this movie in case you haven't looked at it enough, and I would like to stop there. Thank you very much, please.
Thank you very much, Oleg. I think there's some time for questions. Yes, over here.
I have two questions. One is about, you said that you do the the searching for transients on multiple time scales. So does it actually exhaust the parameter space? Like, do you exhaust the times of transients? And my second question is that whether after flagging out that transient source, did you achieve a high dynamic range image of the old friend or the old devil?
Yeah, okay. Yeah, excellent question. I'll answer the second one first. No, because I only found this like last week or 2 weeks ago. So it's the top priority on my list to re-image the data now with having flagged out the satellites, because I am very curious. You know, I spent such a long time trying to get a good map that it would be nice to get one out now. Your first question about timescales. So the timescales is just a list. I haven't thought about this very hard, but I think that if we start from the raw cadence and then we search all the timescales in increments of 2, we should probably cover the entire parameter space. And of course, what we actually do here is, maybe the slide doesn't explain it. What we do is we make the raw cubes, and then we actually smooth them with Gaussian filters to those various timescales. I suppose if you were looking for transients where you expected a particular type of light curve, you could design a better matched filter. And then we could add that kind of matched filter to Tron. But basically the idea is you have this filter bank of time filters, which in the first version are just Gaussian kernels, and you apply this filter bank to your raw data.
Thank you.
Thanks. Over there.
So nice talk. So what is the self-calibration strategy that you guys use? Because if you use the global continuum model to self-calibrate, and depending on the solution interval that you have used, would it not suppress the flux of the transient sources? So what is the strategy that you use?
Yeah. There's actually, if you look at this paper, there is a bit of a discussion in there about exactly this issue. So yeah, there's a global continuum model. Generally, I try to avoid amplitude calibration because MeerKAT amplitudes are very stable anyway. So we just do phase and delay. And if the field contains sources subject to direction-dependent effects, then we do peeling, but with longer solution intervals for precisely this reason. But basically the general answer is you try to self-calibrate the best way you can, as you normally would, but be very mindful of solution intervals, yes.
Thank you.
I don't think there's another question, but I have a question for you, Oleg, on the polarization. You didn't mention it too much. Of course, we had some conversation on this some months ago, but maybe you can say a bit more about polarization, because especially if you have scintillation and maybe exoplanets, as you mentioned, right? There will be a lot of interesting stuff happening in the other Stokes parameters as well.
Yeah, that's right. That's right. So we actually do in Tron, we do if the polarization is available, then we do the search in full Stokes when we make the residual cubes. We haven't found anything that in polarization that we haven't found in total intensity yet, but certainly we put in polarization searches exactly for the reasons that you mentioned. There are, of course, some interesting issues with polarization because, you know, if I show you, for example, the dynamic spectra of the parrot, here is Q and U, right? There's a lot of Faraday rotation across the band. So if you just do a wideband image in QU, all of this is going to get washed out. You're not going to detect anything. So to really detect things in polarization, we also have to go to coarser, to finer channelizations, right? At the moment, we're doing wideband images and doing the detection of wideband images. In the next version, we're going to start splitting out the band to subbands and looking for things across frequency as well. The imaging, of course, is highly parallel. That's no problem. But then you got to do the search. Of course, as you can imagine, if you have a dynamic spectrum like the one on the right here, I mean, this scintillation is bright enough that we are detecting it even in wideband. But you can imagine a fainter scintillating object which would be detectable if you correctly looked across frequency as well, but wouldn't be detectable if you did a wideband light curve.
Yeah.
So
Okay.
all these things still need to be done.
Okay, thanks. Let's thank Oleg again and all the speakers of this morning's session.